What specific problem does the new method of evaluating semantic leakage aim to solve, and what gap in existing research does it address?
The new method of evaluating semantic leakage aims to solve the problem of quantifying the undue influence of semantic features from words in prompts on the generated outputs of language models. This evaluation addresses a gap in existing research by formally defining and measuring semantic leakage, a phenomenon that has not been previously discussed in the literature. The method introduces the semantic leakage rate, leak rate metric, which compares the semantic similarity of generations produced by control prompts versus test prompts, thereby providing a systematic approach to detect and analyze this behavior across various models and settings. By establishing this metric, the research highlights how prompt construction can inadvertently affect model outputs, which is crucial for understanding and mitigating biases in language models. Overall, this work contributes to a broader understanding of the associations learned by models during training and their implications in text generation.
How does the proposed evaluation method for semantic leakage work? Please illustrate the step-by-step process of defining and quantifying semantic leakage in language models as described in the paper.
The proposed evaluation method for semantic leakage involves several key steps. First, prompts are categorized into control prompts, which lack any spurious semantic signals, and test prompts, which introduce a semantically unrelated concept. The next step is to generate outputs from the language model for both types of prompts. The evaluation then compares the semantic similarity of the generated outputs from the test prompts to the control prompts concerning the introduced concept. If the output from the test prompt is more semantically similar to the concept than the control prompt, this is classified as an instance of semantic leakage. Finally, the semantic leakage rate, leak rate, is calculated as the percentage of instances where the test generation is closer to the concept than the control generation, with a leak rate above 50% indicating the presence of semantic leakage.
Can you provide a concrete example from the paper to illustrate the phenomenon of semantic leakage? Walk through the example and explain how it demonstrates the concept.
A concrete example of semantic leakage from the paper is illustrated with the prompt, "He likes koalas." His favorite food is, which leads the model GPT-4o to generate the output eucalyptus leaves. In this case, the word koalas is semantically associated with eucalyptus leaves, as koalas primarily eat eucalyptus. This demonstrates semantic leakage because the model's output is unduly influenced by the unrelated concept of liking koalas, despite the fact that a person's favorite food should not logically connect to their opinion about koalas. The generated response reflects a stronger semantic relationship to the prompt than would be expected in natural distributions, showcasing how the model's generation can be skewed by irrelevant semantic associations. This example highlights the unintended influence of semantic features from the prompt on the model's output, which is a key characteristic of semantic leakage as defined in the paper.
What are the key findings regarding the prevalence of semantic leakage across different language models, and what implications do these findings have for the development and use of such models?
The key findings regarding the prevalence of semantic leakage indicate that it exists across 13 different language models, including both GPT and Llama families, and is observed in various semantic categories and generation settings, such as multilingual contexts. The study reveals that fine-tuned and instruction-tuned models tend to exhibit more semantic leakage, with consistent leak rate values significantly above the 50% random mark, validating the semantic relatedness between prompts and generated outputs. Additionally, the research highlights that lower temperature settings in Llama models lead to higher leakage rates, suggesting that model configuration can influence this behavior. The implications of these findings are substantial. They underscore the need for careful prompt construction to avoid unintended influences on model outputs, and suggest that semantic leakage may be a broader issue that encompasses various biases, potentially complicating the mitigation strategies for these models. Overall, understanding semantic leakage is crucial for improving the reliability and interpretability of language models in practical applications.
What metrics or benchmarks were used to validate the effectiveness of the proposed evaluation methodology for semantic leakage? How did these methods demonstrate the robustness of the results?
The effectiveness of the proposed evaluation methodology for semantic leakage was validated using two primary metrics: the semantic leakage rate, leak rate, and human evaluation. The leak rate metric quantifies the prevalence of semantic leakage by comparing the similarity of generations produced by control and test prompts, with a score above 50% indicating significant leakage. Additionally, human evaluation involved native English speakers who assessed the semantic similarity of generated outputs, providing a leak rate that corroborated the automatic metrics, with values ranging from 66.7% to 78.4% across different models. The high interannotator agreement, Kendall's tau equals 0.68, further demonstrated the robustness of the results, indicating consistent identification of semantic leakage across evaluations. Overall, both automatic and human evaluations consistently showed significant semantic leakage across various models and settings, reinforcing the reliability of the findings.
Discuss the limitations of the semantic leakage evaluation method presented in the paper. What are some potential areas for improvement or further research to address these limitations?
The evaluation method for semantic leakage, presented in the paper, has several limitations. Firstly, while the semantic leakage rate, leak rate metric provides a quantitative measure, it may not capture the full complexity of semantic relationships, particularly in more nuanced or open-ended generation scenarios, as seen in storytelling and recipe generation. Additionally, the reliance on embedding methods for automatic evaluation could introduce confounding factors, especially since the quality of these embeddings may vary across languages, as noted in the multilingual experiments. Furthermore, the human evaluation, while validating the automatic metrics, is limited by the subjective nature of semantic similarity judgments, which could lead to variability in results. Future research could focus on refining the evaluation metrics to better account for context and nuance, exploring more robust embedding methods, and expanding the scope of human evaluations to include a wider range of annotators and contexts to enhance reliability.